When I was a kid, I did something that, looking back, feels almost embarrassingly sincere. I took a cheap plastic ruler, laid it on a paper map of the Milky Way from a science magazine, and started measuring how far it would be from Earth to a star with a pretty name. I do not even remember which star. I just remember tracing that line in pencil, then going to the back of the magazine to find the little scale. This many centimeters equals this many light years. I did the conversion like a tiny accountant of wonder. I multiplied. I wrote the number down, then I sat there, staring at it, because my brain quietly refused to care. It was like trying to picture how heavy a mountain is. You can say the words, you can write the digits, but nothing inside you moves. So I cheated. I turned that distance into something familiar, I thought. If I had a spaceship that could go as fast as a jet, how long would it take? I did more multiplication. The answer was so stupidly big that I crossed it out and did the math again, convinced I had misplaced a zero somewhere. I had not. That was the first time I felt the universe push back against my imagination, not with a philosophical argument with arithmetic. Years later, after surviving university, after being broken and rebuilt by real physics instead of glossy magazine diagrams, I realized that moment with the map was my first encounter with a very specific kind of disappointment, the one where your intuition picks a fight with the structure of reality and loses. You know that intuition I am talking about, the one that helps you catch a falling mug without thinking, or squeeze through traffic without dying, or judge whether you can jump the last 2 stairs without snapping an ankle. That gut feeling is a masterpiece of evolution. It is the result of millions of years of trial and error on one small planet, in one narrow band of temperatures, at one gentle gravity. But that same gut feeling is hopelessly, laughably unqualified to comment on galactic distances or relativistic velocities or the energy budget of a starship. It is like asking your family dog to explain quantum mechanics. The dog might be very good at being a dog. That does not mean you should put it on a thesis committee. Still, we keep doing it. We take those savannah instincts, point them at the night sky, and let them declare verdicts. Surely there must be others. Surely they could come visit. Surely, if we just try hard enough, we can go to them. I became a physicist, partly because I loved those questions, and partly because I wanted permission to keep asking them as an adult. But physics did not give me comfort. It gave me something harsher and, frankly, more honest. It gave me the reasons why the spaceship in my childhood map will never leave the page. Let me be clear about what I am and am not saying. I am not saying that interstellar probes are impossible. We have already thrown tiny machines out of the solar system, and with better engineering we can throw better ones faster and farther. I am also not saying that it is physically forbidden for bits of matter to travel between the stars. Rocks do it, dust does it, photons do it all the time. What I am talking about is the dream you and I actually care about, the one with people aboard, a ship with a crew, or at least something intelligent, something that remembers where it came from and why it left, making a deliberate journey from one star to another and arriving in a condition that still counts as alive and sane. That is the dream inside almost every science fiction story. That is the dream in the back of your mind when you look up at Orion and feel that strange, mixed ache of possibility and loneliness. And that is the dream that physics, very slowly and very patiently, takes apart. Not because the universe is cruel, because the universe is consistent. I want to walk you through that dismantling. Not by repeating the same path you usually hear, where someone lists a bunch of technological obstacles like bullet points in a depressing presentation instead. I want you to come into the lab with me. Metaphorically, I want to show you the parts of physics that seem at first to have nothing to do with spaceships. Little mundane pieces, a clock on a table, a heated wire, a grain of sand, and then I want to widen the frame until you see how those same small rules, scaled up, quietly murder the fantasy. If we do this right, you will not just know, in an abstract way, that interstellar travel is practically impossible. You will feel why. It will slot into place in the same deep, uncomfortable part of you that once thought, as a child, that space was basically just a big ocean and then had to grow up. Let us start not with distance or speed, but with something more innocent. Let us start with time. In the lab where I worked as a graduate student, there was a narrow metal shelf with maybe a dozen different clocks on it. Cheap digital ones. An old mechanical one that ticked so loudly it drove everyone insane. A pair of synchronized laboratory timers that cost more than my first car. They were not there because we liked being punctual. They were there because relativity is not just about stars bending light. It is about the way time itself behaves when you move and when you fall. The first time you encounter this in a serious way, it feels like a magic trick. You learn that if you put one clock on the floor and one on a tall shelf, and you are absurdly, obsessively careful with your measurements, you can detect that the lower clock is running a little more slowly than the higher one. Not a lot. Not enough to change your day. Just enough that over a year of careful observation, the difference between the ticks adds up to something you can no longer ignore. Why? Because clocks, like everything else, live inside space-time, and space-time is warped by energy and mass. The closer you are to the Earth, the deeper you are in its gravitational well, and the more time itself stretches. This is not an exotic effect happening far away near a black hole. This is happening to you right now. If you spend your life in a basement apartment, you will age very slightly less than someone who spends their life on a mountain peak. Once you swallow that, you learn another bite of the same meal. If you take one of those clocks, strap it onto a jet, fly it around the world, and then bring it back, it will have ticked differently than its twin that stayed home. Motion itself, when fast enough, also fusses with the passage of time. We build our global positioning system on this fact. If satellites did not correct for both the gravitational and the motion-induced distortions of time, your phone would not know where you are. The guiding equations of relativity are baked into the infrastructure that helps you find the nearest coffee shop. This is the first quiet betrayal of your intuition. You have lived your whole life assuming there is one universal now. That what is happening for you is in some cosmic sense happening for everyone. It is wrong. The universe slices reality up into different sheets of time depending on where you are and how you move. To get between stars, you have to lean hard on that weirdness. You have to accelerate, coast, at some fraction of light speed, then slow down again. People love to talk about the time dilation you get as a bonus. Go fast enough, and less time passes for you than for the people you left behind. You turn the ship into a kind of one-way time machine to the future. At first, that sounds like a hack, like a cheat code for distance. Sure, the star is 400 light years away, but if you go close enough to light speed, maybe the whole trip will feel like just a few years to you on board. You come back. Everyone you know is gone. Society has moved on. Your favorite band is now an ancient classical reference. But from your perspective, you made it. You beat distance by leaning on time. This is the version of the story that your inner science fiction reader loves, and mathematically, there is even some truth to it. If you are willing to burn utterly ludicrous amounts of energy, you can ride that relativistic effect and make your personal clock tick much more slowly than the clocks back home. Here is the part that does not make it into the optimistic narratives. Time dilation does not get you around the cost of acceleration. To get into that weird regime where your clock is crawling and everyone else is racing ahead, you first have to brutally, mercilessly force your ship up to a significant fraction of light speed. That means you have to pay the full energy bill. Relativity does not give you a free ride. It just lets you choose which frame of reference gets to call the trip short. There is a famous thought experiment where you imagine using a constant gentle acceleration on your starship, maybe the same acceleration you feel from gravity on Earth, so that you can walk around the cabin like normal. You accelerate for half the journey, flip the ship, and decelerate for the other half, always feeling that comfortable 1 gi under your feet. Do the math, and in your own personal frame of reference, you can cross ridiculous distances in what feels like a reasonable time, a human lifetime to go to the center of the galaxy. A few decades of ship time to reach other galaxies. People hear this and latch onto it like a loophole. But then you put on your physicist hat and you ask an unromantic question. Where does the energy come from? This is where those boring lab clocks and the equations that govern them become a lot less cute and a lot more vicious. In the world you and I navigate every day, the relationship between speed and energy feels friendly. You push a car, it speeds up. Push twice as hard, it speeds up twice as much. That is Newton talking, and Newton is good enough for traffic laws and water balloons. As you get closer to light speed, Newton quietly leaves the room and Einstein takes over. And Einstein has no interest in preserving your intuitive comfort. The kinetic energy of something moving relativistically does not scale nicely with speed. It explodes. Every little addition of velocity takes more and more energy than the last. You can think of it as the universe charging you an ever steeper price the closer you get to its ultimate speed limit. You never quite reach that limit. You can get absurdly close, 90% of light speed, 99%, 99.9%. Each extra decimal place costs you an almost comically greater amount of energy than the last. The bill climbs toward infinity long before you hit the final wall. Now remember our constant acceleration fantasy. If you want your ship to feel like Earth gravity for months or years, you are not just doing one brutal burn at the start and one at the end. You are constantly pouring energy into the ship to keep up that acceleration, building more and more kinetic energy over time to make that happen. You need fuel to carry that fuel. Your ship needs to be larger. The larger the ship, the more energy required to accelerate it. The more energy you need, the more fuel you have to bring. We are back in that vicious loop you saw hints of earlier, but now it is plugged into relativistic dynamics instead of a simple back-of-the-envelope rocket equation. At a certain point, the theoretical exercise starts spitting out numbers that are not just impractical, but absurd. To push a ship with even a modest mass to a speed where time dilation really starts working in your favor, and to do it in a way that is tolerable for any kind of living or even delicate mechanical system, you need energy on the scale of what stars produce over years or centuries. This is not poetical exaggeration. You can actually run the numbers and compare. The total yearly energy usage of our entire civilization is tiny compared to the energy just one star emits in the same period. Now imagine harnessing the output of thousands or millions of stars to accelerate one ship, while also wasting a big chunk of that energy just throwing fuel out the back for propulsion. Take a step back and look at that picture. Somewhere in a galaxy there is a civilization sophisticated enough to capture and direct the energy of stars. Maybe they have built structures around their suns to drink in most of the light. Maybe they are tapping into black holes. However they do it, they control fire on a scale our species has never even approached. And they decide to spend that treasure not improving their own environment, not building digital utopias, not solving whatever existential problems they have at home, but pushing a chunk of metal and meat across interstellar space, where it will spend centuries or millennia in transit, vulnerable to every hazard the void can throw at it. For the privilege of arriving at some random ball of rock that may or may not even be habitable. Do you feel the mismatch? This is the second betrayal. We like to imagine that more advanced means more capable in every direction, but more advanced also means better at arithmetic, better at cost-benefit analysis. The very same intelligence that allows a species to reach for the stars also allows it to realize that, energetically, a starship is a borderline insane investment. And this is before we talk about the smaller, nastier killers. Not the towering cliffs of relativity and thermodynamics, but the gravel underfoot. The little hard realities that tear up your boots long before you reach the cliff. Let us leave the lab clocks and the energy graphs for a moment. I want you to picture something concrete. Imagine you are standing in front of a wind tunnel. Inside is a long, narrow chamber where engineers test airplane wings. Right now it is empty, and the air is still. You are holding a single grain of sand between your fingers. If you let that grain of sand fall, it drifts down lazily. You can barely hear it tick against the metal floor. Now someone walks over to the control panel and turns on the wind. It starts light, then ramps up, you watch flags shake, loose cables strain. The air shoots down the tunnel faster and faster. If you drop that same grain of sand into the gale, it whips away. Hit by that much moving air, it would sting your skin. If you are reckless enough to stand in the blast, it will feel like needles. Increase the speed again, beyond anything any airplane on Earth would ever face. Take the air in that tunnel to a significant fraction of light speed, if you could somehow do that without everything catching fire. Now ask yourself, what would that same grain of sand do if it hit you? It would not sting, it would not bruise. It would punch through you like a bullet. It would deposit so much energy so quickly that flesh and metal would flash to plasma. One fleck of dust at that speed is not a nuisance. It is a high explosive interstellar space is not empty. It is thin, but not empty. There is dust, there are atoms, there are lonely ice pebbles, fragments of forgotten collisions. At the velocity you need for even vaguely reasonable interstellar travel, that environment becomes a minefield. You can try to shield your ship, but every bit of armor you add is more mass. More mass requires more energy to accelerate. More energy means you have to work harder to reject waste heat, which is another unglamorous problem that does not get nearly enough stage time in science fiction. When you use energy, especially at the scales we are talking about, you produce heat. You have to get rid of that heat, or your systems cook. In space, you cannot just dump it into air or water. You radiate it away as light, which is a painfully slow process. The bigger and hotter your ship, the more radiating area you need, the more fragile fin-like structures you have to expose to that hostile dust and radiation. So now, your interstellar arc is not a sleek dart hurtling through the void. It is a bloated, delicate, heat-bleeding monstrosity covered in radiator panels and sacrificial shielding, lumbering along constantly on the brink of either freezing or boiling parts of itself. When we zoom in on these engineering constraints, we have not even mentioned the passengers. You have probably seen old footage of fighter pilots in centrifuges, their faces squashed by acceleration, voices distorted into uncomfortable squeaks. Those are modest G-forces. Astronauts experience a few times Earth gravity during launch, and that is already pushing the limit of what is safe and comfortable. To ramp a starship up to a significant fraction of light speed, in a time that does not involve generations living and dying on board, you either accept brutally high accelerations for extended periods, which will turn all but the hardiest organisms into paste, or you accelerate more gently and pay in travel time. The universe almost always offers you this kind of trade. You can save time if you spend more energy and accept more risk, or you can save energy and reduce risk if you are willing to let time stretch toward the meaningless. There is a reason that almost everything that moves across cosmic distances in reality is not alive. Photons do not care how long they travel. Dust does not complain about G-forces. Comets do not feel boredom, a human being does. If you are still with me, you are part of a very small, very stubborn minority. Most people quietly bail out long before this point, not because the material is too difficult, but because it is too indifferent to what they want. You and I would love it if the universe bent, even a little, toward what feels narratively satisfying. An enormous stage full of civilizations meeting, clashing, trading, colonizing, a big galactic society. The space opera version of a crowded city instead. We keep discovering that the stage is gargantuan, the lights are dim, and the actors are pinned down at home by the same simple, heartless equations. In the first half of this journey, we talked about time, energy, acceleration, dust, and heat. We looked at why pushing a ship to interstellar speeds without killing what is inside is not just a matter of better engines, but of running into the basic accounting rules of space-time. Now I want to turn to something that feels softer at first glance, more philosophical, less about fuel tanks and more about meaning. But if you follow it all the way down, it is just as sharp. I want to talk about information physics in its modern form is obsessed with information. Black hole theorists debate whether information about particles that fall in is lost forever. Quantum computer people torture delicate systems of atoms to squeeze out a few fragile bits of computation. Thermodynamics, The same field that tells you engines can never be perfectly efficient has been reinterpreted as an accounting system for knowledge. Here is the weird unifying thought. Every time you think about moving matter around, you are really thinking about moving information around. The shape of something, its composition, its arrangement in space, all of that is information. A human brain is a three-dimensional object full of that kind of structured information, the pattern of which neurons connect where, the strengths of those connections, the constantly shifting dance of electrical and chemical signals. That is you. Strip away the poetry and the metaphors, and that is what your memories and personality boil down to, a fantastically complicated physical arrangement sustained over time by metabolism. When we talk about putting a person on a starship and sending them to another star, what we are really talking about is transporting an incredibly intricate, extremely fragile, highly organized lump of information across hostile emptiness without mangling it beyond recognition. This is much, much harder than sending a crate of metal bolts. In the world of computers, we already know how delicate information can be. A single flipped bit in the wrong place can crash a program or corrupt a file. To protect against that, we use error-correcting codes. We store multiple copies. We design systems that can notice when something is wrong and fix it on the fly. Now scale up from a computer hard drive to a starship full of complex life, and from a service life of a few years to a journey that might last centuries or longer. Depending on how you choose your trade-offs, everything in that ship is under permanent attack by entropy. Heat rattles atoms out of place. Radiation shoves particles through circuitry and DNA. Chemical reactions slowly degrade materials. Mechanical stress builds up in structures. On Earth, we fight these enemies with maintenance, redundancy, and resupply. You can swap out dying components. You can bring in fresh food, spare parts, and new people. You can patch the ship of Theseus piece by piece forever, as long as you have a planet-sized support network behind you. A true interstellar voyage cuts the cord. Once you are out beyond the Oort cloud, there is no resupply. There is only what you brought, and what you can scavenge in environments that are unimaginably thin and empty compared to your home. You might respond, fine, let us send machines. Let us send something purely digital, something that can repair itself. A swarm of nanobots, a cloud of self-replicating probes. Take the squishy humans out of the loop. Even then, you do not escape the tyranny of information. Our self-replicating machine is a physical embodiment of a recipe. The instructions for making more of itself are encoded somewhere, maybe in a molecular pattern, maybe as digital firmware. That recipe has to remain legible through countless cycles of wear and repair, or the descendants that arrive at the destination after 1,000,000 years of hopping from rock to rock will have mutated into something else entirely. There is a sneaky parallel here with biology. You and I exist because a chain of replicators has survived and copied itself generation after generation for billions of years. At each copy step, there is a chance of error. Most errors are lethal or pointless. A few are helpful. That is evolution. On an interstellar scale, any self-replicating probe you send out becomes subject to a similar process. Its blueprints are not sacred. They will drift design decisions that made sense in your original context back home may become obstacles in some strange new environment around another star. By the time your machines arrive, they might no longer be obeying your intentions in any recognizable way. They might not care that you wanted them to send a postcard home. They might have diverged into a local ecological niche, a robotic lichen clinging to an alien asteroid, having long forgotten the dreams of their ancestors. So maybe you decide, forget replication, let us just harden one vessel as much as possible. Make it a vault of information, a library on a trajectory between stars. This sounds more manageable, but now we bump into the most fundamental constraint of all, one that threads through thermodynamics, computation, and even the way black holes behave. It is called the finite capacity of a system to store reliable information in the presence of noise. Every physical system has a limited ability to keep bits distinct from one another as time and random perturbations gnaw at them. You can reduce the error rate by spending more energy on shielding, on cooling, on error correction, but you can never drive it to zero. Over long enough times, even the best protected memory will start to blur. The speed of light, that famous limit, is part of the same story. It is not just an arbitrary number. It is the rate at which causal influence can move through space-time. It sets the maximum speed for any signal that could, even in principle, be used to coordinate repairs, to check in, to compare copies, and fix discrepancies. If you send something far enough away, fast enough, you lose the ability to keep it synchronized with its origin. It becomes its own world, with its own errors accumulating, its own mutations playing out. This is not just a logistical problem, it is a deep statement about how the universe handles knowledge. The farther apart two places are in space-time, the more independent their internal bookkeeping becomes. The dream of a tightly linked galactic civilization, updating itself like a distributed computer cluster, runs straight into this wall. Even if you somehow built a network of light-speed or near-light-speed communication channels between stars, every message would arrive aged, out of date. You could never have a truly shared now. Imagine trying to run a society under those conditions. Laws, culture, language, technology, all of it drifting at different rates in different pockets. By the time a response arrives to some crisis, you broadcast it from your world has moved on, for better or for worse. At that point, you can ask a harsh question. What does it even mean to speak of one interstellar civilization? Is it not more honest to speak of multiple loosely related civilizations, each bound more tightly to its own planet and its own local past than to anything out there in the dark? You might be tempted to shrug and say that is fine. Even a loose connection is better than isolation. Who cares if the reply takes centuries? At least someone is listening. But remember our earlier discussion about asynchronous lifetimes. Stars have deep, leisurely timescales, civilizations, as far as we can tell from our single data point, do not. Our species has been playing seriously with electricity for a few centuries. We have been sending radio messages into space for barely more than one. We have been capable of ending ourselves with nuclear weapons for about as long. The lifespan of a technological phase may be just a tiny flicker in the lifespan of a planet. So any signal you send now is a message in a bottle that may wash up on a shore long after the sender has vanished. The answer, if it ever comes, will arrive for someone else, a different culture, perhaps a different species, descended from, or replacing the one that spoke. This is the third great betrayal. We are wired emotionally to expect feedback. You speak, someone hears, you reach out, someone takes your hand on human scales. That expectation is reasonable. On interstellar scales, it is almost comical. The universe does not guarantee conversations. It barely guarantees monologues. Which brings us to the way all these threads knot together. Interstellar travel, as people usually imagine it, is not just a technical project. It is a psychological bomb. It is a story we tell ourselves about escape and expansion. If things go bad here, we will go there. If we are alone here, we will find company there. If we stumble here, surely someone wiser out among the stars will have answers. Physics quietly burns that story down. The energy requirements and the time dilation tell you that moving bodies between stars at humane speeds is fantastically, almost offensively expensive. The dust and the radiation and the wear and tear tell you that keeping those bodies, or their mechanical stand-ins, intact and meaningful along the way, is a never-ending war with entropy. The finite speed of information and the finite lifespan of civilizations tell you that even if someone makes the effort, their arrival or their message is unlikely to line up neatly with your moment of need. There is no cavalry on the horizon. The horizon is too far, and the horses are bound by the same light speed limit you are. When people point to mysterious lights or blurry videos and say, "But what about them?" Surely that proves someone is already here. I understand the yearning underneath it. It is the same longing I had as a child with the ruler and the star map. amplified by adulthood and fear and hope. But then the physicist part of me wakes up and starts running the numbers. Any craft that could come here from another star in less than geological time has to solve the exact set of problems we have been talking about. It has to accelerate and decelerate huge masses without liquefying its contents. It has to shield itself against dust impacts that would make meteors look gentle. It has to manage heat with exquisite care. It has to endure long stretches of isolation and repair. It has to carry an energy source comparable to a small star without that energy announcing its presence in spectacular ways. When you stack all that up and compare it to what we actually observe in those videos, which are grainy, ambiguous, lacking all the collateral effects that real physics would demand, the scales tip. You do not need to invent new laws of motion and new forms of energy and new kinds of matter to explain a blurry spot on a camera feed. You do need all of that and more to justify the idea of a ship casually popping in and out of our atmosphere as if it just took a shortcut off a galactic freeway. This is not about being a killjoy. It is about refusing to downgrade the universe to fit our favorite stories. When you let the real laws of physics speak, you get something stranger and in a quiet way more humbling. You get a cosmos where life might exist in many places, but almost all of it is effectively marooned, where the speed of light is not a cruel prank, but a boundary condition that makes consistent histories possible, where time flows in such a way that cause leads to effect locally, while distant events blur into a kind of unreachable background. You get a situation in which every world that manages to produce consciousness is, for all practical purposes, on its own. That sounds bleak until you turn the thought around. If no one is coming to rescue us, then we are terrifyingly the adults in the room. There is no higher authority, no galactic council, no advanced species who have already solved climate change or war or inequality and will arrive any day now to share the patch notes. There is just us, on this odd little planet with its fragile atmosphere and its volcanic politics, trying to figure out how not to fumble the only known example of complex life. That realization can feel like grief. You have to let go of a whole category of comforting fantasies. But once the grief passes, something else can take its place. Responsibility value. If Earth were one of a million waypoints on a crowded interstellar trade route, just another gas station with a pretty sky, then the destruction of its biosphere would still be tragic, but it might feel less uniquely obscene. Someone, somewhere, would still be singing. In the picture physics gives us Earth is not a gas station. It is closer to a solitary research outpost in a howling wilderness. The lights are on. There are organisms here doing outrageous, improbable chemistry. There is a species here building telescopes and arguing about ethics and drawing little maps of the Milky Way with plastic rulers. As far as we can tell, that is not normal. It is spectacularly rare. Every barrier that makes interstellar travel a nightmare also acts like a shield around this rarity. It prevents easy exploitation. It prevents easy conquest. It prevents the sort of casual, routine access that would reduce us to a resource or a curiosity in someone else's empire. We are isolated, but isolation and protection in this context are not opposites. They are nearly the same thing. When you look up at the night sky knowing all this, the silence hits differently. It is not just an absence of radio chatter or starships. It is a statement about how the universe has chosen to arrange its stage. The actors are spread impossibly far apart. The scripts do not sync. The curtain for each local drama rises and falls without crossovers. That can make you feel small. It can also, if you let it, make you feel indescribably lucky. Because against odds that we do not yet fully understand, on a rock that is just the right size at just the right distance from just the right star, the chemistry to build eyes and hands and brains and rulers and star maps happened anyway. Physics is merciless about what it forbids. No faster-than-light travel, no free lunch and energy, no cheating on entropy. But it is also generous with what it allows, given enough time and enough randomness. It allows suns to burn steadily for billions of years, It allows heavy elements to condense out of supernova debris. It allows water to exist as liquid, ice, and vapor in the narrow band of temperatures our planet occupies. It allows, once in a while, something that can look up and ask why. Knowing why interstellar travel, in the sense we dream of, is effectively impossible does not make the universe smaller. It makes our understanding of it sharper. It forces us to place our hopes and our efforts not in some imagined exodus, but in the one place where our actions clearly matter, here. On this world, in this thin envelope of air, under this one small star, we can still listen to the sky. We can still send probes on one-way journeys. We can still search for the faint signatures of others doing physics in their own corners. That search is worth doing, not because we expect a reply in time to help us, but because understanding is a kind of survival in its own right. When you know the rules of the game you are playing, you can at least stop wasting time, hoping they might secretly be different. So the next time you find yourself outside on a clear night, and you feel that ache in your chest, that mix of wonder and loneliness, let it come. Let your inner child hold up the invisible ruler and trace imaginary lines between stars. Then let the physicist in you gently take the ruler away and show you the equations instead. Not to crush the dream, but to rewrite it. The real story is not that the cosmos is teeming with travelers who have somehow chosen to ignore us. The real story is that we are one of the very few, perhaps the only, places where matter has learned enough about itself to understand why it is stuck at home. There is a strange dignity in that. We are not the junior species waiting for the elders to arrive. We are the experiment that succeeded against staggering odds, now faced with the uncomfortable awareness that no one else is coming. That means the task of not wasting the next few centuries falls on us. The physics that makes interstellar travel impossible is the same physics that gave us this chance. We do not get to rewrite those laws. We do get to decide what we do with the tiny pocket of freedom they leave us.